bonding models. In a covalent species, covalent, so this like the atoms shared their electrons. Electrons are shared between atoms. In ionic species, one or more electrons transferred between atoms to form ions. So we have two types of bondings models, the covalent and the ionic. Covalent means sharing. Ionic means transferred. Transfer both electrons to one of the atoms to form ionic molecule. Molecular structures are based on applying wave mechanics to molecules. This provides answer as to how and why atoms are combined. So Lewis structure, very popular, how atoms bonded in a molecule. Lewis presented simple useful method of describing the arrangement of valence electrons in a molecule by using dots or crosses to represent the number of valence electrons. Okay, so Lewis used the crosses or arrows or dots to describe the bonding. Electrons in a molecule should be paired. If a single electron left alone, it means the atom is radical, very active. So when there is a single electrons left over by atom or a molecule, so that atom or molecule will become a radical. Radical means very active and it's unstable. Single, double, and triple bonds represented for H2O, nitrogen gas, oxygen gas. Okay, so we come to take an example of oxygen, atomic number 8, electron configuration 1s2, 2s2, 2p, 4. 2, 2, 4 will be 8. So if we come to the hydrogen, each hydrogen atomic number is 1. So it's 1s1. The other hydrogen in the water is 1s1. So we have 1 oxygen, 2 hydrogens. Now let's combine together and see how the bonding forms. So the oxygen, we said the last main shell, electron 2 and 4 would be 6. So 2 and 4, 6. To reach a stable molecule, octet rule, so it needs, oxygen needs another 2 electrons from 2 hydrogens to be 8 electrons in the central atom. So these 8 electrons, we still used 1 electron from hydrogen to 1 electron from the oxygen to form single bond. Oxygen, hydrogen, single bond. And another 1 electron from oxygen with 1 electron from hydrogen to form another single bond. So every single bond is formed by 2 single electrons. Now, if 2 and 2 here, these are the bonding for the single bond and single bond. 2 electrons, 4. So how many remaining from the 8? Remaining 4 electrons. These 4 electrons will do 2 lone pairs. 2 lone pairs. 2 free pairs of electrons. So you can draw, this is the Lewis structure, either using dots here using crosses, bonds, or rows, and the dots. So now if we see the structure of the water, it's an angular structure. There is an angle here. Angular structure, and we have two lone pairs stabilize the structure. Now we come to the nitrogen to see what is the bonding between nitrogen. Nitrogen have 7 electrons, the other one 7, 1s2, 2s2, 2p3, similar. So the last valence electrons, the last main shell is number 2, and it has 2 and 3, 5. 5 for this nitrogen, 5 for other nitrogen. As we said, 1s2 are the core electrons. They don't involve in reactions, only the final main shell could do reactions. So now what we have 10 electrons. How can we bond 10 electrons? So here we have the 2 electrons for nitrogen. This is 2s2 here, and this is the other 2s2 here. These are the two electrons in the s orbital, in the second orbital, this one, and this is the 2 electrons in nitrogen. How many left? 3 and 3, 6. So these 3, 6 will be 3 lone pairs, and the 3 lone pairs can form 6. 6 can form triple bond. So if we just rearrange these dots to become like this, so every 2 electrons will do single bond, single, single. Every single bond formed by 2 electrons. So how many single bonds we have here? 3. So these are the 3. So the bonding between nitrogen are a triple bond, and we have 2 free lone pairs. 2 free lone pairs. Okay. Now, so if we've been asked what are the bonding between oxygen and hydrogen in the water, we could say 2 single bonds and 2 lone pairs. What is the type of bonding in the nitrogen gas? It's a triple bond, and we have 2 lone pairs. We come to the oxygen. So what is the bonding type between oxygen gas? So oxygen atomic number is 1s2, 2s2, 2p4. And the other oxygen number, the same thing. So now we have these 2 electrons for each one of them, and we have 4 and 4, 8. So 8 electrons, 10, 12 electrons. We have in total 12, 6 from here, 6 from there. 12 electrons, what they can do? They will form, okay, 4 of them from the P will form 2 single bonds. So each 2 electron, one from oxygen, the other from the other oxygen, similar, another bond. Of course, this has been like viewed or analyzed by a crystallography method to find exactly this application of the oxygen gas, and they found there is a double bond between the oxygen. So every double bond is formed from 2 and 2, 4 electrons. And these 4 electrons, later on, we will find they've been involved from the p orbital. And the other, so we have 4 electrons out of how many? Out of 6 and 6, 12. 6 and 6, 12 electrons. 4 How many left? 8. So these 8 will be 4 lone pairs. 2 will be localized on this oxygen, this 4, and this the other 4. So now the bonding between oxygen is double bond and 4 lone pairs. And the oxygen is very active. It's very good for combustion, for burning fuel, for breathing, for saving people in accidents. They give them oxygen. Why oxygen is active? And it's open the chest and the breathing cells, and will give energy to the cells, and the patient will breathe normally after giving him pure oxygen for a time being. Not always, because oxygen can be used for burning, but with little amount if inside our body. So now, what is the type of bonding between oxygen and oxygen gas? We say it's a double bond, and we have 4 lone pairs. Each lone pair, 2 electrons. So now we come to the summary knowledge. Single bond formed by 1 electron from atom and 1 electron from another atom. So these 2 will be as a single bond. The lone pair formed by 2 electrons to be free, which gives polarity to the atom, and they will be one beside one. Not like the single bond will be one far away from the other. Assigning oxidation states. So oxidation states can be assigned to any atom in a compound. Oxidation state is a number of charges the atom would have in a molecule or ion if electrons were transferred completely. So we can find oxidation states when the electrons been transferred completely in a molecule. Elements can have one or more oxidation state. It depends on how electronegative its bonding partners are. So it could be more than one oxidation state. Oxidation state depends on electronegativity. Most electronegative elements are usually assigned a negative oxidation state. Why negative? Because they gain electrons. Rules for assigning oxidation state: electronegativity and valence electrons. Fluorine, F, is the most electronegative element, fluorine. So if we come to the atomic number of fluorine is 9, 1s2, 2s2, 2p, 5. So we have 7 valence electrons at the outer shell, 7. Let's put the 7 beside the fluorine. So 7, we can leave them as 3 lone pairs and 1 single electron. We come to the oxidation state of fluorine, always -1. Always minus. Why? Because it's taking this electron from the other atom to be beside it, and the fluorine will obey the octet rule, will be more stable. So the fluorine, if you see here, the p orbital is occupied by 5 electrons. So how many maximum electrons can p occupied by? The maximum is 6. So what does it need? P5 needs only 1 electron to be saturated, to be stable. So the fluorine always take or gain 1 electron to fill the p orbital. So the p orbital after filling will become 6 electrons in, and 2 from S will be 8 together. So 8 means very stable. And so the oxidation state of fluorine always -1, except when bonded to another fluorine atom. Okay, then oxidation state for each will be 0 in F2. Why is 0, as we said before? Because it will be partially giving the electron from fluorine to a partially electron lost by other fluorine. So partial will be covalent bond between fluorine and the fluorine gas will be bonded singly, and it will be 0 oxidation state overall. Okay, so fluorine and fluorine here, as you see, this has 7 electrons, this has 7 electrons. So these 2 single electrons here, they just stays where they are, and they will share the bond, a single bond. So it will be 1 bond, single, formed by 2 electrons, and the other 3 here, 6 electrons as 3 lone pairs. 6 electrons as 3 lone pairs. Now, both of them look like they are octet rule. Okay? Because this is being partially moved, but not completely. So here we have, and here, if there is another different halogen, can take the electron for the fluorine, because the fluorine and the other halogen will be different in electronegativity. Always for fluorine, gain the electron, take electron, but not in fluorine gas. BF3. Now we come to BF3. So the boron in the middle. Let's see how many electrons in boron. 5, 1s2, 2s2, 2p, 1. So how many electrons we have at the outer shell? We have 3. We call them the valence electrons. 3 valence electrons. So 3 valence, what does they need? They need 3 fluorines. So the fluorine will come with 7 electrons. 3 of them lone pairs, 1 is single. So this single electron from outer shell, if you remember, fluorine, here they have 7. 7 means 3 lone pairs and 1 single. So here you can see 3 lone pairs and 1 single. This single electron can gain another electron from boron and to form single bond. The boron will give all 3 electrons to the fluorine. 3 electrons will do 3 single bonds, whereas the other 6 electrons for each fluorine will form 3 lone pairs free, not for bonding. When I say free, it means it's not bonded. So BF3 structure is, you see, this is the structure of it, and a boron in the central atom lost 3 electrons for the fluorine. So the fluorine will become 3 minus or 3 or minus a 3. Fluorine oxidation state here is 3 minus. Why? Because it gained 3 electrons from the boron, 3 fluorines. Each fluorine gained 1 electron, so there are 3. So the each fluorine is -1. 3 of them will be -3. So overall, now we come to the overall charge, because fluorine came with has single electron. Boron had 3 single electrons. In total, boron will be +3, and the boron charge must be plus 3. Fluorine, 3 fluorines will be minus 3. So minus 3 plus 3 will be 0. So the overall charge in BF3, you see there is no charge outside, means stable, 0 charge after reaction. Similarly for NF3. Oxidation states for elements in their elemental state, 0. This is a law. So copper, lead, aluminum, iron, any other atom, on its own, pure, it will be, oxidation state will be 0. Also, homogeneous gases oxidation states are 0. Any homogeneous means the same type of atoms. Here are oxygen, oxygen, so 0. Fluorine, fluorine, 0. Hydrogen, hydrogen, 0. So all the overall charge in the oxygen, it will be 0, even with the presence of 3 lone pairs, 2 lone pairs by 2 lone pairs and the other force making a double bond. Still, we can say the overall charge for these gases in the homogeneous method will be 0. Now we come to the monoatomic ions. Oxidation states equals to the charge on the ion. Sodium, calcium. So each sodium ion can lose 1 electron, become positive charged. So the oxidation state of the sodium will be +1. Calcium can lose 2 electrons to become +2, and the oxidation state will be 2 plus. Hydrogen usually assigned oxidation states of +1 hydrogen, usually. If it goes with a different atom, will partially lose the electron, so it will become +1. So exceptions, when tended to another hydrogen, as I said now, hydrogen and hydrogen will do single bond, and this single bond will form H2. It's a neutral molecule or no charge. When bonded to metals, which are less electronegativity, like we see the lithium, electronegative is 1, but the hydrogen electronegative is 2.1. So in this case, we have lithium hydrogen different in electronegativity. So lithium here will be +1, and the more negativity hydrogen will become -1. Bear in mind, the oxidation state of the lithium will be +1. Hydrogen here will become -1. Why? Because the lithium will lose the electron and the hydrogen will gain this electron because of different electronegativity between hydrogen and lithium. Which one is higher electronegative? That will be minus charged. Ozone or ozonide anion, O3 minus. Let's check it out. Here, every oxygen is -3rd. So 3 oxygens types -3rd will be -1. Each oxygen in oxygen is formally -3rd. So this is the first time we can see the 1/3. It means a third, and it's been found by crystallography analysis. They found the oxidation state for each oxygen in the ozonide ion. They found it as -3rd. It's not even a 1. So 3 oxygens times 1/3 will become -1. So overall charge of the ozonide, -1. Elemental forms of oxygen, dioxygen, ozone. Now you tell me, what's the oxidation number or overall oxidation for the oxygen gas? 0. What is the overall charge for ozone molecule? 0. 0 for the for the ozone. It's stable. It's in the atmosphere outside the Earth, and it's protecting us from the UV of the sun. That's the ozone layer. So oxygen and ozone molecule charge formally is 0. They are neutral. In most of its compounds, oxygen usually has an oxidation state of -2, with some exceptions. Let's check the superoxide anion, O2 minus. So why minus is here? 2 oxygen should be each one of them half minus oxidation state. Okay, each oxygen is formally minus a half. So minus a half times 2 atoms will become -1. So the superoxide anion is O2 minus 1. Peroxide anion, H2O2, you remember, peroxide. If we check because of 2 hydrogen here, so 2 electrons will go to the oxygen, and the oxygen, both of them will become -2. So here, as you see, the overall charge of peroxide, anion in hydrogen peroxide, -2. Each oxygen is formally -1. Inside the H2, you see, this is exceptions. Here are some exceptions. In the peroxide, hydrogen peroxide, if you've been asked, what is each oxygen in the hydrogen peroxide oxidation state? So you just look at the hydrogen. You have 2 hydrogens. So the left side of the molecule, if I do it like this, the left side of the molecule, H2, the right side is O2. So it should be why there is no charge on this molecule together, because they are 0. So how come this becomes 0? Let's go inside. If we know the hydrogen oxidation state here is known, but the unknown for the oxygen. So the hydrogen here, the oxidation state of the hydrogen, each hydrogen is +1. 2 times +1 will be +2. So this oxygen 2, all of it should be -2. Okay? So if I put it like this, now this side, 2 hydrogen times +1, okay? That's to the left. And to the right, I have 2 oxygen times, I don't know. So the unknown is the oxidation state of each oxygen. So here to the left would be +2, but to the right should be -2. So how come I can replace the question mark by which number to become -2? I can put -1. So -1 times 2 will be -2. that will equalize the +2 to the left. Why? Because the overall charge is 0. When there is a 0, the left side of the molecule +2, the right side should be -2. How can I get -2? Is the oxygen should be each oxygen -1. So I can replace this by -1, and you can see now 2 times +1, and here 2 times -1 +2 -2. If you put them together, will become 0. We end up with 0. So here, the oxidation state inside the hydrogen peroxide is -1 for each oxygen. Oxidation state for halogens usually -1, except when bonded to fluorine, oxygen, occasionally nitrogen, or higher halogens. So we can get NaCl here, the sodium +1, chlorine -1. Why? Because the sodium lost 1 electron to become positively charged. Chlorine gained this electron to become negatively charged. Chlorine has an oxidation state of -1 here in the chlorine anion. Let's come to CCl4. So in tetrachlorocarbon, here we can see the chlor charge is what? The chlor, all of them -4. -4. Carbon must be opposite charge of +4. Must be +4 because the chlorine got 4 electrons from the carbon. So the carbon lost 4 electrons, and the 4 chlorine got 4 electrons in total. So now each chlorine here will become what? -1. What each chlorine -1? Let's see here. So the carbon 6,1s2, 2s2, 2p2. So we have 4 electrons in the outer shell, 4 valence electrons. The chlorine ending with 7 valence electrons. So what's the carbon needs 4 chlorines, and the structure here is tetrahedral, and you can see 7 electrons for the chlorine, 7, 3 lone pairs, 1 single, 3 lone pairs, 1 single, here the same. So the single electron will gain 1 electron from the carbon. The carbon is very stable, you know. So in nature, stable and has 2 oxidation states, +2, +4. So here we have 4 electrons from outer shell to do 4 single bonds. These are single bonds, 4. 1, 2, 3, 4. If you see this kind of rows, it's just like it's in a 4 dimensions. So we can draw them like this. Otherwise, you can draw 4 single electrons, single bonds, as we know, like this one. Chlorofluorine here. Now you can see fluorine is high electronegative. So it will gain 1 electron from the chlorine. So the chlorine will lose 1 electron to become positive. Fluorine gain electron to become negative. So now the bond between them, we have, you remember 7 by 7 electrons, 6 electrons as 3 lone pairs, 1 single electron left. Same as here. So we have 3 lone pairs free, 3 lone pairs free, 2 electrons forming single bond. OCl minus, now you can see here the oxygen minus 2. So the chlorine should be, you see this minus here. So I have 2 minuses for the oxygen. So it should be, the chlorine should be 2 plus. But here you have the minus, so remaining 1 minus. So now the chlorine inside OCl minus, oxidation state is +1. You see the chlorine? +1, because the oxygen has 2 minuses. So here the oxygen is more powerful and oxygen more electronegative if we check 3.5 than chlorine 3. So which one more electronegativity will gain the electron? Gain it. So and become minus charged. So here for the first time we can see the chlorine is +1, and then because +1 and over here -1, so they could be the chlorine is +1 and the oxygen -2. Oxygen assign negative oxidation states. The higher electronegative takes the minus charge. Okay, oxidation numbers equals charge on an ion, molecule or a group. NaCl sum +1, sodium -1. Chlorine together will become 0. Neutral. Hypochlorite, 2 minus plus 1 positive charge of chlorine become -1 here. Nitrogen trioxide, NO3 minus. As a group, it's minus charge. How? Let's count. Nitrogen outer shell is 1s2, 2s2, 2p3 to become 7. So I have a 3 and 2 will be 5 electrons outside the nitrogen. 5 electrons in the outer shell plus 3 times -2 is 6. So +5 -6 together to add will become -1. So this -1, I got it from inside here oxidation number. 3 times -2, -6. Nitrogen has 5 electrons outside. So all the charge will become -1 as a group. For all group is -1. Nitrogen pentaoxide, N2O5. Now let's count why it's neutral and 0. 5 times -2, 2 times 5 plus 5. Here will become 10 minus 10 plus, together 10 minus 10 plus will become 0. So there is no charge on N2O5. Potassium permanganate, similar thing here. If we do the oxygen, you see potassium is +1. Manganate, MnO4 should be -1. Why? Let's check it out. So 4 times -2. Manganese is missing. Let's say it's unknown. And we have +1 for the potassium. So now, +1, -8. What's the difference between -8 and +1? Will be 7. 7. So 7 and minus. So the oxidation number for the manganese will become +7. Okay. plus 7. Now, if you want to calculate potassium plus 1, manganese plus 7, O4 minus 2. So every oxygen minus 2 times 4, 8. 8 in minus. Potassium and manganese plus 7 plus 1, 8 in plus. 8 minus and 8 plus together will become 0. So the overcharge of KMnO4, there is no charge. It will be 0, should be 0. And now you see overall charge of the group of the permanganate should be minus 1. And here the manganese surrounded by 7 electrons, 3 of them lone pairs, 1 of them single. So this single electron will form single bond with oxygen to become single bond, but the others will form double bond. You remember the structure? Double bond, double bond, double bond, and single. Now this is very stable, and outside here we can find the potassium. So the potassium outside is a plus 1, the permanganate minus 1. Together they will delete each other and become 0 charge, as you see. But K2MnO4, what is it? Now, let's check what is the oxidation number of the manganese inside K2 potassium permanganate. Okay, we come here. The manganese is missing. We can do question mark on the manganese. Oxidation state of the oxygen is minus 2 times 4, minus 8. 2 times plus 1 for the potassium, plus 2. So we have 2 and 8. What is the difference between them? Is 6. 6 in minus. So the manganese will become 6 plus. Now, you put the 6 plus here in the equation, 6 plus and 2 plus, 8 plus. Oxygen minus 2 times 4, 8 minus. So 8 minus and 8 plus will become 0. So the overcharge of the potassium permanganate will, in this molecule, is 0. So as you see, there is a 0 manganese charge in manganese oxide, calculated as O2 is minus 2. So the manganese should be plus 2. And to be like 2 times minus 2 minus 4, the manganese here will be plus 4. So the overall charge will be 0. Manganese dioxide, 0. Why? Because the manganese here is plus 4. Oxidation number. Perchlorate, minus outside. Let's calculate how this minus came out. We see the oxygen, we know oxygen oxidation number minus 2 times 4, minus 8. Let's come to the chlor. Chlorine outside plus 7 electrons. You remember, one has to do the halogen always outside, 7 electrons. So 7 electrons, take out 8 electrons for the oxygen, 1 is remaining. The 1 should be in minus. Okay, so now metals, always positive charge, oxidation state. Non-metals, positive or negative. But always metals, positive charge. Why? Always losing electrons. They don't gain. Sodium fluoride, plus 1, minus 1. You see? 0. H2O, minus 2 for the oxygen. 2 times 1 plus for the hydrogen. Overall charge will be 0. A group, similarly, you can count You can practice this to see SO4 minus 2, Y minus 2, 4 times minus 2, oxygen minus 8. Sulfur outside 6. So the difference between 8 and 6 is minus 2. Here we have, again, 2 times 6, 12. 3 times 2 minus 2 minus 6. And 12, 6. So, and here between these two, the difference is minus 2. And this minus 2 will go to the group for the whole group. So inside the structure here for S2O3 is 2 double bond, 2 single bonds. And here SO4 is 2 single bonds and 2 double bonds. And so on for the others. You can calculate here always 0, 0 overall charge. Sometimes here we have a nitrogen and hydrogen, so they are partially negative, partially positive. But why? Because they are covalent bonds. But here they are ionic bonds, complete transfer of electrons. Here there is no complete. They are covalent. Covalent, you use partial charge. Ionic, fully charged. What is the overall molecular charge for this? So the overall charge for this is minus 2, 0, minus 3, 0, plus 1, minus 1, 0. Straight away.